Hello and welcome back to our discussion about operating system support and virtual memory. As we are getting into understanding how does virtual memory work, it is useful to know some of the physical principles of how do the memory and storage devices work. So let's start with the memory. Memory, in this case, dynamic random access memory, or DRAM for short, is built in a different process than our logic process. It is also a CMOS type of a process, but it is optimized differently. DRAM has special DRAM bit cells. Those are the cells optimized in a technology that store 1 bit of information. On the other hand, logic process is optimized for speed, interconnect, and also for logic density. As a result, when we compare DRAM bit cell with an SRAM bit cell, we find out that the DRAM cell is much smaller. SRAM cells are those that are being used for building microprocessor caches, and DRAM is our external main memory. In comparison, DRAM is almost 10 times denser than the SRAM. So when we look at the modern microprocessor, we'll find in its spec sheets that it has perhaps tens of megabytes of cache. On the other hand, a DRAM chip with about the same area may have more than 10 gigabits of DRAM cells on it. So technology for all DRAM chips is pretty much the same or very similar to each other, but their protocols or interfaces that they use for talking to the microprocessors and the packaging may differ. So in this case, we are looking at a type of DRAM that is used in desktops and servers. It is so-called DIMM, or a dual inline memory, that has 8 or 16 DRAM chips on this small printed circuit board that plugs into a desktop or a server. Anybody who has built a homegrown workstation or a gaming rig has done that, inserted these DRAM chips into the motherboard. On the other hand, most laptops nowadays don't really have room to fit these DRAMs. Instead, the DRAM chips are soldered directly onto the motherboard. In this case, we have a bit older version of a Microsoft Surface Book that has these orange chips, which are DRAM chips, soldered onto the motherboard, very close to the microprocessor. By the way, take a look at this microprocessor. This is an Intel microprocessor from a few years ago. The microprocessor was here and it had 2 layers or 3 levels of cache on it, and there was a last level cache that was built in the DRAM process as a separate chip next to the microprocessor on the same package. And then when we get to cell phones, we perhaps see a third incarnation of DRAM. In case of mobile phones like Apple iPhone, and in this case a few-year-old Apple A12 Bionic, fits 4 DRAM chips on top of it. So it uses these DDR interfaces, which is a protocol that is one of the protocols that is used for talking to a DRAM. 4 DRAM interfaces connect to 4 DRAM chips that are placed on top of the microprocessor. So regardless of a packaging, all DRAM chips and all DRAM memory is volatile. What does that mean? That means when we turn off the power, it forgets. So all the data that is stored in DRAM is lost. It is the same for both DRAM and SRAM. Microprocessors need power to retain data in their caches, so do DRAM chips need supply voltage to retain the data that is stored in them. So that's why we call them volatile. Now, some of the characteristics of DRAM: latency to access the first word is roughly 10 nanoseconds. And when we compare that to a processor speed, that's like 30 to 40 processor cycles. Can be more or less depending on the class of DRAM and the speed of a microprocessor. Then important thing to notice that each successive read or write is much faster if we are writing to a nearby place on the DRAM. So each successive read or write happens every 0.5 to 1 nanoseconds. In every access we bring 64 bits, and DRAM typically supports something that is called the burst mode, meaning that we can typically do these bursts of 8 or 16 reads or writes, which would essentially bring 8 or 16 times 64 bits and fill a cache line. Now, going back to just a few words about volatility, DRAM is a little bit more volatile than the SRAM. And what does that mean? Well, SRAM will retain data as long as the supply is on, but DRAM forgets. That's why it's called dynamic random access memory. The data is stored dynamically in the form of a charge, and the charge may leak away from the DRAM cell. So it needs to be refreshed. So every few hundreds of milliseconds, this controller that lives on the microprocessor accesses DRAM, reads the contents, and writes it back into the DRAM. That's a process of refresh. Processor doesn't have to do anything with that. It's a function of the controller there. That's it. That's what we need to know about the memory. Let's get into the storage. Storage is what we typically call the disk. And there are two types of disks that we will encounter: solid-state disks and hard disk drives. They're both attached as a peripheral I/O device using some of the principles that we have kind of outlined, but we're going to discuss more in a couple of lectures. Both SSD and HDD are so-called non-volatile memory types, which means they retain the value even when the power is off. That's very convenient, otherwise our computers would be forgetting everything. We would have to load the operating system and everything into the drives every time we would like to boot them. SSD and HDD have very different characteristics and different price. SSD is a lot faster, so each access is something like 40 to 100 microseconds, meaning it is slower than the DRAM, significantly slower than the DRAM, taking, say, 100,000 processor cycles to access the SSD. HDD is even slower. It takes like 3 to 10 milliseconds to access a sector in a hard disk drive, which corresponds to a couple of tens of millions of microprocessor cycles. But there is also a big difference in price. According to today's data or today's prices, it's about 5 times. SSD is about 5 times more expensive than the HDD. SSD also comes in different shapes and forms. It can be in this shape that resembles the shape of small disk drives, hard disk drives, or it can be in more modern one, M2 forms. A few notes about disk drives and why are they so slow and why is data so cheap there. The disks are mostly mechanical, they're electromechanical, very sophisticated electromechanical systems that store data in iron oxide, like rust. So there is a platter here that is spinning, and there is a mechanical arm that flies over that surface and magnetizes the data, magnetizes the surface to store the data. Conversely, when it is in a read mode, it just hovers over the surface and reads the data. Now, these magnetic domains are so small, they're like a few nanometers on the side. So in order to recognize the bits, this arm flies a few nanometers above the surface. I mean, it's a really sophisticated technology, you know, pretty crazy stuff out there. Data is generally organized in so-called concentric circles, or called tracks, this arm is suspended, and again, as I said, flies over. It's actually designed like a wing, and it flies over the surface of a disk. There are disks come again in different classes. Most of them go from 7,200 RPM to 10,000 RPM. There were some that were built with 15,000 revolutions per minute. That's really, really fast. I mean, it's like not quite a dental drill, but like a Ferrari. So if you convert that in milliseconds, it takes about 6 milliseconds per revolution, which means that for this kind of a disk, average random access time will be 3 milliseconds or so, maybe a little bit less. For a typical disk drive with 7,200 RPM, it'll be about 5 milliseconds. That is why this corresponds to 10 million processor cycles. Now, when we take these apart, it's really fun to understand how they work and why they're actually so slow, because they're mechanical. I took this video, which is very good, from Nick Parlanti, that I encourage you to watch entirely, where he discusses the operation of disassembles the hard disk drive and operates it with the lid open. Remember, they're not in vacuum because that head needs to fly over the surface, so it needs some air. If you look at it, he opens it up over here, so you can see the spindle, the head, and he plays with it. And then you can see, when you go towards the end of the video, you can see it in action. In this case, it is most likely copying a file from one location to another. So you can see the arm moving it from, like physically moving a file from one track to another. A few other notes about that. These drives come in different sizes, and I know a lot about drives because I used to work. I designed read channels for these drives. This is a 3.5-inch disk drive, which was typical for desktops. And when I designed that chip, it's actually in these more modern drives, they're flipped, the board is flipped inside out, so you could see who made the read channel. And I used to go to Fry's and flip every single drive to see if they have my chip on it. This is more of a laptop drive that is 2.5-inch, and when they got in this race, when these drives got in the race with solid state drives with flash memory cards, they made really these 1-inch drives. There is an actual real moving disk inside. This was like a 2 GB micro drive that would go into cameras. So speaking about flash memory and solid state drives, now there is nothing mechanical in there. Solid state drives are built of something that is called the flash memory. It's kind of similar to our DRAM, except the technology is different. It is built out of these non-volatile cells, so you somehow trap the charge inside the cell. In DRAM, you just store the charge, and here you trap it such that it stays inside the bit cell, even if we turn off the power. In organization, it's kind of similar to DRAM, but it's just packed really densely, even denser than the DRAM. It is fairly fast. It's a lot faster. It's slower than DRAM, but a lot faster than the disk. But the key thing is it's organized such that we always read and write blocks. We never access bytes or words. And it has some unusual requirements. If you want to erase it, if you want to set everything to 0, you have to erase the whole block. One thing that people kind of are mistaken, because of this trapping of the charge, the flash drives have a limited lifetime. So you can completely erase them only a few thousand times nowadays, and there are spares and stuff like that, spare blocks and spare sectors on that drive to extend the longevity. But solid-state drives are generally less reliable than the mechanical hard disk drives. One thing with flash drives, their flash memory, it is kind of a miracle of technology really nowadays. It has become very cheap, and it really is not slowing down with scaling. Although we can't make these individual bit cells much smaller in area, what this industry have been doing is stacking them on top of each other. So you kind of see these silos now. There is an array of cells in each layer, and then they stack layers on top of them. I think now current production is 128 layers, but I think 256 layers are coming in now. So that basically extends the technology scaling. So flash memory is going to continue going in the third dimension for years to come. And that's it. We are going to get more into virtual memory after a break.